Welcome to online lecture series in organic chemistry. In this video, I am going to start the new chapter, molecular orbital theory for coordination compounds. In molecular orbital theory, or according to molecular orbital theory, the molecular orbitals are constructed by the combination of atomic orbitals as per LCO principle, that is linear combination of atomic orbitals principle. So according to MOT, combining atomic orbitals must have comparable energy, proper symmetry, and there must be appreciable overlapping. And as you know, the molecular orbitals are formed by the combination of atomic orbitals. There is a combination of atomic orbitals which results in the formation of molecular orbitals, and the equal number of molecular orbitals are formed as that of the atomic orbitals involved in the combination. For example, if 4 atomic orbitals are there, then molecular orbitals will be 4, like that. Out of various molecular orbitals, some orbitals are bonding, some are anti-bonding, some are non-bonding orbitals. Normally bonding molecular orbitals have lower energy, anti-bonding molecular orbitals have higher energy. So this is about the general molecular orbital theory concept. But when we apply this molecular orbital theory for coordination compounds, then some additional assumptions we need to consider, and the main assumptions of molecular orbital theory to apply coordination compounds are: the first important assumption is the central metal ion in coordination compound contribute 9 atomic orbitals. For example, 5 d orbitals, 1 s orbital, and 3 p orbitals. So 5 d orbitals, that is dxy, dyz, dzx, dx square minus y square, and dz square. These are the 5 d orbitals. 1 s orbital, that is 6, and 3 p orbitals, px, py, pz, 7, 8, 9. So in this way, central metal atom or ion contribute 9 atomic orbitals. This is most important thing. Actually, molecular orbital theory not only considers the atomic orbitals of central metal atom or ion, but also considers the atomic orbitals of ligand. So this is also important. In crystal field theory, only the orbitals of metal ion are considered and not ligand, but MOT considers the atomic orbitals of metal ion as well as ligand orbitals. Okay, so first postulate is metal ion contributes 9 atomic orbitals, 5d, 1s, and 3p orbitals. Especially when the 3D transition element involved in the process of formation of coordination compound, then the orbitals contributed by 3D element is 5 3D orbitals, 1 4s orbital, and 3 4p orbitals. In this way, that transition element contributes 9 orbitals. Now out of these 9 atomic orbitals contributed by metal ion, 6 orbitals of metal ion, for example, dz square, dx square minus y square, s, px, py, and pz, these 6 atomic orbitals of metal ion are suitable for the formation of sigma bond, because these orbitals are oriented along the axis in the direction of ligands, which can cause positive overlap. Okay, whereas remaining 3 orbitals, that is dxy, dyz, dzx, these orbitals are suitable for the formation of pi bonding because these three orbitals are oriented in between axes and have lateral overlap. So this is the first assumption of the molecular orbital theory applied to the formation of coordination compound. Now second assumption is each ligand must possess at least one filled sigma orbital. This is the second postulate. Already I told you MOT considers the atomic orbitals of metal ion as well as ligand orbitals. So as per second postulate, each ligand must possess at least one filled sigma orbital. So there are 6 ligands in octahedral complex. So each ligand contribute one orbital. Altogether there are 6 ligand orbitals, and each ligand orbital contain 2 electrons. Okay, this is the second assumption or postulate. Now third assumption is the 6 ligand orbitals initially combine with each other to form a set of ligand group orbitals, that is LGO. And the fourth postulate is each metal ion orbital now combine with its matching ligand group orbital to form bonding and anti-bonding molecular orbitals. And last postulate is once the bonding and anti-bonding molecular orbitals are formed, electrons are then distributed in bonding and anti-bonding orbitals on the basis of Hund-Solop maximum multiplicity and Pauli's exclusion principle. So these are the assumptions of the molecular orbital theory applied to the coordination compounds. So first important assumption is metal ion contribute 9 orbitals. Out of 9 orbitals, 6 orbitals are responsible for sigma bond, and the orbitals are dz square, dx square minus y square, that is Eg orbitals, s orbital, px orbital, py orbital, and pz orbital. This is the first postulate. Second one, each ligand orbital or each ligand must contain at least one filled orbital. Next is the 6 ligand orbitals combine with each other and they form the ligand group orbitals. Next postulate is each metal ion orbital now combine with ligand group orbitals and form bonding and anti-bonding orbitals. And last postulate is there is a distribution of electron on the basis of Hund-Solop maximum multiplicity and Pauli's exclusion principle. Now various orbitals of metal ion and their symmetry symbols are s orbital, it is non-degenerate orbital, and its symmetry symbol is A1G, and this s orbital, it is responsible for the formation of sigma bonding. Now px, py, pz, these 3 orbitals are triply degenerate p orbitals. Symmetry symbol is T1U, and this is also responsible for sigma bonding. Dx square minus y square and dz square, these 2 orbitals, their symmetry symbol Eg. This is the set of the doubly degenerate d orbitals, which is also responsible for sigma bonding. And dxy, dyz and dzx, these 3 orbitals, these are triply degenerate d orbitals. Symmetry symbol is T2G. These 3 orbitals, these are not involved in the process of formation of sigma bond, but as these are oriented in between axes, there is a lateral overlapping and responsible for pi bonding. So these are the metal ion orbitals, 9 orbitals, 1s, 3p and 5d orbitals. Altogether 9 orbitals comes from the metal ion. Now here G stands for Girard and U stands for ungirard. T, it's triply degenerate, E double degenerate. Okay, so these are the symmetry symbols: A1G, T1U, EG and T2G. When A1G symbol is there, then you memorize it is, or there is involvement of s orbital. When T1U comes, there is involvement of p orbitals, Eg dx square minus y square and dz square, and T2G dxy dz dzx. So in next video we are going to discuss the identification of central metal ion orbitals and their symmetry suitable for the formation of sigma bonds with ligand orbitals.